All right,
Thanks,
Chris.
Roland. Thanks, Roland. Good. Okay, so I've got my screen up there now. Thanks, Roland, for the introduction. Thanks, Joe for the talk he gave earlier. If you're watching this recorded later, you may want to take a look at Joe's talk. I'm going to refer back to some of the things that he said. I'm going to go through a implementation of a call spread that we wrote here at Agoric.
And Chris, you may want to zoom in a little bit as well. The text is a little small on YouTube, if you don't mind.
I already made it small. It's such a tiny window to look at all this code.
All right, best of luck.
Yeah, I'm used to using my full big screen to look at code, and looking at it through a tiny little window. I'll try and make do with this. This is an implementation of a call spread, as Joe Clark explained earlier. In my presentation of this contract, I'm going to talk about two major topics, each with a bunch of bullet points. The first overall topic I'm going to talk about is standard features of Zoe contracts. There are a lot of things that every Zoe contract needs to do, and so I'm going to go through how this contract interprets the terms, how it builds invitations, in this case, how it calculates the payoffs, how we do the reallocation. The second topic is the unique aspects of this contract. Every Zoe contract is going to have some things that it does differently. Why else would you have a new contract? You must be doing something that's unusual. There are a couple of things that are unusual about the call spread. It uses promises in a way that we hadn't seen before in contracts. I'll explain why and how we do that. And it uses the price authority, which is a kind of an oracle. And I'll talk about how the price authority feeds into this and what it does. So I'm going to start with the standard features of Zoe contracts. Actually, I think I'm going to start with I'm going to switch screens quickly and talk about what this contract does in the context of the call spread, and I've got a different screen to show with that. There, this one. So, now Roland has to bring up this window. So this is just a different version of the diagrams that Joe was showing in his presentation. It shows the price of the option call spread changing as a function of the underlying. So this is what I've implemented is a fully collateralized call spread, which means that prior to selling the contract, the two parties combined have put in the full price of the underlying, the full price that would be paid out later. The thing I want to point to here is that the thing that the contract has to implement is that at the closing time, the contract talks to an oracle to find out what the price was, and then it has to figure out whether the price is below K1, in which case the long side of the long position will get the totality of the collateral, or if it was above K2, above the second strike price, then the short position will get the entirety. And if the price is somewhere between K1 and K2, then we have to do this linear calculation to figure out how much to give to each of the parties. And so that's the calculation that the contract has to make, and that figures in a couple of ways. One is that there's a bunch of the code that you'll see that's about making sure that this happens at the right time, and then there's figuring out the right price and allocating it to the right party. So back to the code. Take just a second. I only need 6 clicks to do that. There, that's still back to the code now. Let's start with the high level. As I said, the things that every contract does. I've collapsed a bunch of code here. There's a couple of comments that I've collapsed and some other things. The main thing I want to start with is the shape of every Zoe contract is that there's a start function which takes the Zoe contract facet and does a bunch of things, and then at the end, let's see, I can do this. So my cursor is here, which means that the blue highlight shows that function. And so that function ends by returning a creator invitation. There's a couple of things that are returned conventionally. This contract only needs to return one of them. That's the invitation to the creator who's going to fund the entire contract. And here normally we would only export the start function for Zoe to execute. Here we've also exported another function just for testing purposes. So that's the one that actually does the calculation of the share of the collateral that goes to the long position. So that's the high level external view of that. The first thing that the contract does when Zoe starts it is it deconstructs the terms, pulls out the terms, and it knows. Actually, I've got a comment up here that I had collapsed that shows what the terms are. I don't see it immediately, so I'll go back to the code. Oh, actually, I wrote it here. Here's a listing of what's in the terms for this. As Joe talked through it, there's an underlying amount. We need to get access to a price authority to tell us what the price is. We have an expiration time and a timer. There's K1 and K2 are strike price 1 and strike price 2. And the settlement amount can be in a different currency. As Joe referred to, you can do this in 2 currencies, or you can do this in 3. There's the underlying, there's the collateral, which is the amount that will be paid out, and then there's the strike price, the valuation of the collateral. And here I've actually pulled those out as 3 different currencies. The issuer keyword record shows that there's underlying and strike and collateral. And so Zoe lets us distinguish all 3 of those so that we can pay attention to the prices. And you could make 2 of those be the same currency, but in this case, it's possible for them to be 3 different currencies. So that, for instance, you might have a call spread on the value of Apple stock priced on the NASDAQ, which is priced in dollars, but pays out in Japanese yen, for instance. So that's 3 different currencies, 3 different issuers. So back to the contract itself. We start by pulling out pieces of the terms. We're going to want the amount maths and the brands of some of these different issuers. We then start by asserting that the collateral and the strike math are both, the used as NAT math means that they're fungible currencies. And I only do that for strike and collateral. The underlying doesn't actually have to be fungible. It could be the price of you could be doing a call spread on the price of a magic shield or something like that. There's just one magic shield. If there's a market for it, then you can know what the price is over time and be able to do the math on all of this based on that. So as long as the price oracle is willing to give you a variable price on the underlying, that's all that matters about it. It doesn't have to be fungible. I then assert that the strike price 2 is greater than strike price 1. That's just the nature of the call spread option. If you wanted them in the other order, just name them the other way. That's pretty simple. Here we need, we hadn't needed to do this in previous Zoe contracts, but because of the way we're issuing options to the holders of the long position and the short position, the issuer of the invitation needs to be known to Zoe. I may say more about that later. The way that we're going to implement this contract is that there's a creator who's going to fund the whole thing. That's what makes it a fully collateralized strike. So they're going to put down all of the money behind the contract, and there will be two options created from that let the long party and the short party each have a position that pays off depending on how much what the calculation produces later. And what we're going to do is make a collateral seat that we can allocate the funds to, so that we can assign those funds there and then get them back later. The way that works is I'm back down to the bottom of the contract. We start with make creator invitation is how a Zoe contract goes, and it. So I'm going to collapse the inner handler. So the way make invitation call works, the way make creator invitation goes is it's a JavaScript function that does a bunch of work and then calls zcf.makeinvitation. And there's two sides to what makeinvitation is doing. There's the side from what Zoe sees and the side from what the contract is doing. Zoe is using this in order to return the invitation to the owner so that they can get it back later. And what Zoe does is when you call make invitation, you pass it the handler. Zoe invokes the handler, which does the work and returns the results of that. So in this case, we call that's the inner one. That's this. So what make creator invitation does is it makes the two invitations that will be the assets that the long position and the short position get. Those are pretty simple invitations because all they do is they don't do any calculation. They just give a payout at the end. So the outer invitation makes the pair of invitations figures out the amount of those things so that it can put them in the inner invitations so that the holders of the two, the long position and the short position, can tell what they are. I have a test in which the creator of the outer invitation, let's call her Alice, fully endows the whole contract and then sells one of the positions to Bob and gives the other one to Carol just because that was easier. So when she does that with Bob, Bob can actually look at the invitation and see what the value is. The value is the payout that he'll get later. So all of this is about creating. This is about creating those two invitations. Those are here. So these inner invitations, as I said, they just assign a seat. I'll talk about the promises stuff later. But these make option invitations are really simple. They don't do very much. When the outer invitation creates the inner invitations, this one actually checks the shape of the proposal to make sure that they specified collateral and the two option positions, and then it trades the settlement amount. It assigns, so the trade takes two arguments, a left argument and a right argument, and says what the two seats are. So the creator seat is here gaining the two options, so that those will be there. So that the creator will end up with those in order to be able to hand them out to the two parties that he's giving or selling them to. The collateral seat will end up with the entire collateral, the entire settlement amount, so that it can give them to so they can divide it up among the two parties later. So that's what the invitation looks like. Another piece of the standard part that every contract has to do, as I said, is about calculating payoffs. This payoff calculation doesn't happen until later. So we do some scheduling. I'll talk about the scheduling later, but what I want to point to right now is that at the time that that we get the result back from the payment authority, we'll call this function calculate long share. We'll pass in, I'm going to get rid of this window so that you can see all of this. We're going to pass in the strike math that allows us to do the calculations. If you look at our ERTP protocol, we have these math objects that let us do calculations according to the different currencies. This is a calculation of that has to do with the strike prices, so it needs to be done in terms of the strike math. Other calculations use other maths. I think I showed here we do some calculations in terms of the collateral. So this takes in the current price according to the Oracle, the two strike prices. If the current price is lower than K1, than the first strike price, then the position that we're on in that payoff function is below zero, and so the long party gets all of the money. If the price is above K2, if we're on the upper part of that curve, then the short position gets all of the payout. And if we're in between, then we're taking that proportional function, and what we need to do is just figure out where we are. Take the position of the price between K1 and K2, and take that percentage of the payout and assign it partially to the long position and partially to the short position. That's what this calculation does. So calculate long share comes up down here. This is called in Payoff Options, which is called from the scheduling, which I'm still going to get to later. The reallocate here is it calls reallocate to seed. I've got that collapsed currently. That's part of the promise architecture that's going on here, and so I'll expand that out shortly. I think that's the high-level overview of the pieces of what this contract does that are common to all Zoe contracts. So how we deal with invitations, how we deal with the payoff. In this case, trader real. I'll come back to that. The things that are unique about this contract, first off, because we're giving the holder of the long position and the holder of the short position these options that will pay out later, but that from this contract they don't have to pay anything for. We could have done it with, if it was a margined contract, then each of them would maybe need to adjust their margin as the price changed. But this is a fully collateralized one, so there's no margin adjustments required. And so each of them just gets an asset that is an option that either does pay out up to a certain amount or doesn't pay out at some future time. And in order to make those tradable as Zoe assets, they need to be invitations that you can verify. You can see some of our other talks. We'll talk about how ERTP works. I'm not going to go into that in much detail here. The consequence is that those two options don't exist until they're created inside this function, inside MakeCreatorInvitation. And so okay, the other part that makes this hard is that the holders of those two options, if we tried to require them to exercise their options before the closing time, then we can't force them to do that. And so if we assumed that they did that, then when the closing time came, if they hadn't exercised, we wouldn't have a seat to allocate the funds to. So this contract assumes that they might exercise after the closing time, and in order to make that work, we use JavaScript promises. You saw that up at the beginning. Here, whoops, sorry, I don't mean to scroll around quite so much. At the very beginning of the contract, after we had done the validation, what I use is an underlying function that we have that makes a promise kit which returns the ability to resolve the promise, the ability to reject the promise, and the promise itself, which you can use to get the value that it's eventually resolved to. So I store each of those, one for the long and one for the short, so that I can use them again later. And that means that this reallocate to seat, which is going to get called when at the closing time, that one is here, that's the one I collapsed. What it actually needs to do is, sorry, this is scrolling faster than I expect. What it needs to do is get that promise back out of the array that I stored it in and wait for it to be resolved, which most of the time is probably going to be before the closing time, but it might not. And in the case that it's not before, then we have to wait for that to be exercised in order for the seat to be available, and then we can do the settlement at that point. And the way that we do the settlement is we get the settlement amount from the terms. So share percent, so reallocate to seat was called from down here. So this function is called once we have the price quote. Actually, I need to go back even one more step. Let's do this. So this is where we schedule the payoffs. We did that just as soon, sorry, scrolling slowly. There. So this is in the very beginning MakeInvitation. As soon as we stored the collateral amount in the collateral seat, the settlement amount in the collateral seat, we also schedule payoffs. And schedule payoffs is here. This goes to the price authority, which is a kind of a price oracle. It's built on top of the Chainlink oracle. Patrick Collins will be talking about connecting up Chainlink oracles tomorrow morning, so you can watch that talk. Or if you don't watch this talk until later, you'll be available already. So the price authority that we've written wrapped around the Oracle API has a method called quoteAtTime, which takes an expiration time. The authority has its own clock that it uses. We pass in the underlying amount, which the price authority is required to know how to price. We pass in a brand so that it can tell us what the price is in the strike issuer, and this quoteAtTime function will eventually, we do this E of terms.price authority, which means that it's an eventual call, and so this schedule payoffs returns immediately, but this then function isn't called until the price authority returns a quote at the expiration time. And so when that happens later, this calls payoff options. It will have the price quote was the return value from quote at time. And so we're going to pass that quote amount into payoff options. So at some future time, we'll know the value that's available, and this will take that, and using the two strike prices, it will call that calculate long share function that I showed you before, passing all of these in. So this will give it the position from 0 to 1 that's due to the long share. Inverse is basically 1 to 100, because inverse assumes that it's a percent, and will just give the short side 100 minus what the long side gets. Then we call reallocate to seat. Remember, all of this is being called after quote at time return to value, but reallocate to seat is called at a time when we can't be sure that the holder of the option has actually exercised yet. So we're going to wait for them to exercise their promise. Then we'll have the seat. The share percent will either be appropriate to the long position or appropriate to the short position. They get symmetrical but opposite payouts. And we will then figure out the amount of the collateral that is appropriate to that one. If this wasn't time delayed from the time of the closing, we could have done the calculation once and applied it to both, but the two parties might exercise at very different times, so we have to do the calculation separately for each of them. And then we've got the seat proportion, and then we use trade. With the trade helper function, we can call into Zoe and pass in the gains of each side, and we don't have to say it. The trade function saves some work on the caller's end by requiring that if you say the gains on each side, you don't have to say the losses on the losses for that side. In this case, this seat is the seat that was passed in, the seat that was pulled out of that promise, and they're going to get their portion of the payout. The collateral seats that have been holding on to funds since the contract was created, and it's going to end up with it doesn't gain anything, and trade figures out how to subtract that out, and so it gets whatever remains from that. Then we exit the seat. I keep track of how many seats have exited so that when we're done, we can shut down the contract. We don't want to shut down the contract because the long position has closed or because the short position is closed. We need them both. We need them both to have exercised and been paid off before we close. So that's the scheduling. That's the promises. Let me just walk through the whole thing again and see if it all holds together. I think I've talked about all of the pieces. So up here, those are imports. Here's the comment. I defined some JavaScript constants to label the long and the short position so that I could index them in the array of promises. I already mentioned using the percent calculation for the inverse. I talked through calculating the long share. This is the start contract. Zoe gets passed in. We use the terms to find the math objects and the brand objects that we're going to use. The quote object here was used to create the two options, I think. I told you about the assert. There's the seat. So we had to make an empty seat in order to assign the funds to the seat so that they were available at the end of the period to pay out. I talked about this reallocate. This is the no, this is the one I just did. So this is Payoff Options. We did this so that get the two strike prices. We calculate the long share. We reallocate separately for the two so that they're not connected. I think I got all of this. Let me look and see if there were interesting questions up here. Call spread. Kate answered some of these questions. To be used as digital assets. Yep, I talked about the digital assets. You can't see them here. If anybody asks, I could walk through the test and show how they're used as. Actually, why don't I do that? Here's the test code. Good. This is the test case where we're selling one of the options. So I'm going to skip over a bunch of pieces. Alice is set up. Each of them gets some money in the beginning of this test. We use a manual timer. If you're writing your own contract and it uses oracles or price authorities, you'll need to use a manual timer. The thing about a manual timer is its API from the contract side looks just like the regular one. Sorry, I'm scrolling fast to get down to the bottom of this. But the thing about the manual timer is that the time only advances when you say tick to it. And we found this to be very useful in our tests for building these things. So I'm skipping over this stuff. So Alice creates the instance of the contract. I don't want to talk about this unless somebody asks a question. What I wanted to say is, here's Alice. She is collecting making her proposal, which says that it's what the long amount is, what's the short. So these two options she got from. Oh, okay. I need to go back a little bit. When Alice creates the instance of the call spread, she passes in these standard details and gets back the creator invitation. The creator invitation in its details has the long amount and the short amount, which are the amounts of the invitations that are the assets that the what we call the long seat and the short seat, the two parties that will own the two assets will get. And so her proposal to create this contract is that she wants to get the pair of options. She's willing to provide $300 of collateral, and when she makes the offer, she passes in the invitation that she got. She passes in this proposal, which shows those details. And she passes in the payment, which was created up earlier. That's going to be just $300 because that's her contribution. She gets payouts from this, and that's the two options that hold the payouts for the two sides. And I think she sells the long option, so she's making an invitation here for presumably Bob, because Bob is usually the second party. So she makes an invitation for an exchange in which she's going to give the long option. She's going to ask Bob for $200, and so she does a deposit of the long amount, and oh, I see. In this case, I wrote it so that she sells them both, but I'm only going to show Bob. Bob wants to buy the long invitation. He wants to say this is the long option amount, and he can actually look at that and see what it is. So Bob here makes an offer for that. He pays his $200. He makes his offer. All he has to do is give the payout. And then he'll end up with, he'll be able to extract. So this is where the long option payout is the payout that Alice got, which was passed to Bob, and Bob uses that as an invitation to Zoe. He doesn't pass in. We usually the offer call has an invitation and it has a proposal and it has a payment. But in this case, these two options are already fully collateralized. They're already paid for, so Bob doesn't have to provide any funds. So he just gets the seed immediately for it. He can ask for the payout, and then we have a helper function that lets the test assert that there's a particular deposit. And so in this case, Bob got 225 because the price, I have to go back all the way to the top to see what the terms were. Actually, what I want is the I must have set up a price or price authority here. So what the price authority saw was that the price of the underlying in this case was 2 simoleons, and the price authority is pricing on individual simoleons, and so these numbers are being doubled. This is $40 for 2 and $90 for 2, and the timer is going to expire on the second price here, and so the $90 is going to be between the 2 strike prices, and that's why Bob's going to get 225, and Carol has the other one is going to get 75. So that's a quick trip through here. If there are more questions, I'll be glad to answer them. Otherwise, those are the points that I wanted to make. The call spread option does some unusual scheduling and uses promises for the seats in a way that we haven't done before, but it's fairly standard in the way that it deals with the terms and the way it creates invitations. And like all contracts, it has to calculate payoffs and allocate the outcome to among the various seats. This one ended up using 3 different seats because it has a collateral seat in order to hold onto the funds during the life of the call spread.
Great, thank you, Chris, and appreciate you handling some questions. We did have some come in. Again, for those of you that are watching asynchronously, please do engage with us over Discord. We'll answer your questions whenever you need.
Did you get any in Discord? I only have the YouTube chat up.
No, it's mostly come in through YouTube. But I figure for those of you that do see it later, please send messages in Discord and we can engage.
Yeah. We'll answer questions on Discord later.
Great. Well, Chris, appreciate the time. This is a great walkthrough of an important piece of a DeFi application. So I think we're hoping that those of you in the hackathon working on DeFi projects might be able to leverage this.
Thanks, Roland.